So the topic for today is shear and moment in beams. Let's have an intro. So first of all, okay, I'm gonna talk about your beam. So to define a beam is just a slender bar that carries transverse loading. So there are three types of beams: your pin, as your simply supported beam, your cantilever beam, and then your overhanging beam. So simply supported beam is pin support and roller support. So this is an example of that. So as you can see, a pin here and a roller. So this is a simply supported beam. Next, cantilever. We have a rigid support and a free end. So for example here, this is a cantilever beam and your rigid support, meaning it doesn't allow rotation nor horizontal movement. That's your fixed end. And then you have an overhang, your free end. And then lastly, your overhanging beam, ends extending beyond pin and roller support. So for example, you have your simply supported beam if your beam is only up to here, right? Your pin and roller. But if it exceeds that, you have now an overhanging beam here and here. Now, all of these types are statically determinate because the support reactions here, okay, for simply supported, it's at the spin, roller, fixed end, spin, and roller. Okay, all of those support reactions can be found from your equilibrium equations. Summation of forces x and y and your summation of moment equals 0. So that's your beam. What about the forces on your beam? You can see here, you have different types. So those types are your concentrated load and your distributed load. So a concentrated load is an approximation of a force applied over a very small area. For example here, yeah, that's your point load. Concentrated load as well. And next is distributed load. It is force applied over a finite area. You have two types. You have your line load, which is what we're usually gonna use. It's distributed load that acts over a very narrow area. And then you have load intensity W, marked as W. It is expressed as force per unit length. So Newton per meter or pound per foot. For example, here we have a distributed load denoted by W. Okay. So to convert this, usually you're gonna work with point loads. So when we wanna convert this to point load, just multiply the intensity or W by the length over which your load acts on. Right? Then we have, it's not only, this is an example of uniformly distributed load denoted by this straight line. Okay. Then we have non-uniform distributed load, which looks like this. You also have triangular load, which looks like a triangle, and so on. But again, we won't get too much into that. Okay. So point load, distributed load, point load, distributed load. All right. So the bulk of our topic is talking about shear and moment, both topics which we've already discussed before. So specifically, shear moment equations and shear moment diagrams. So the goal of beam analysis is to determine the shear force denoted by V and the bending moment M at every cross section of the beam. So to do that, we can use a shear moment diagram. So it is a visual reference of the internal forces of a beam. Okay. Then we have the following sign conventions for shear and moment. So for shear, it's positive if the shear forces tend to bend beam element clockwise. Same with moment, okay? It's positive if the bending moment tends to bend a beam element concave upward. So what does that mean? It looks like this. Okay, so if you have your shear force, so to get shear force, you're gonna cut your element or cut your beam. Internal forces would be present. You have your shear and moment. So this is what it looks like for clockwise tendency. So shear here, as you can see, clockwise positive, counter negative. For bending moment, concave upward, positive, concave downward negative. Or if you want an easier way to remember this, if it makes a smiley face, if you bend it towards here, you get a positive bending moment, right? That's what concave upward means. As you can see, if these ends rotate the way it is shown here, your beam will create a smiley face. Alright? Next, let's have a few examples for that. Example 1. So the simply supported beam in the figure carries two concentrated loads. Derive the expressions for the shear force and the bending moment for each section of the beam. And then next, draw the shear force and bending moment diagrams. Neglect the weight of the beam. So let's start with part A, expression for shear end moment for each segment. And what are our segments? First segment AB, then segment BC, and segment CD. So again, our goal is to create an equation for each segment. So let's see. There. So shear moment equations, shear moment diagram. Okay, so let's start with segment AB, right? So for segment AB, again, our goal is to create shear and moment forces for each segment. In short, we're trying to look for the internal forces and internal moment. So from our first topic, can anybody tell me what is the step in order to find out what the internal forces are? What's the first thing to do here? How do I get internal forces? What have we been doing to get internal force for your shaft, compound rod, and those things? Anyone? For example, in your past topics, you have compound rod, right? This is steel, this is aluminum, and there are applied forces here. How do I figure out the internal force for steel? Before summation of forces, what do I get? What should I do first to this? What does this mean? Before we can do summation of forces, I need to, yes, free body diagram, but specifically what? No one? Right. So the answer here is, again, from what you've been doing, you're gonna cut, isolate, right? That's what we've been doing. So cutting steel, okay, draw the applied force, then you're gonna guess your internal force direction. So make an intelligent guess. This needs to be in equilibrium. So I'm gonna guess this is the internal force for steel, okay, towards the left. And then you do your free body, your equilibrium equations. All right. So this is the same thing for beams. So everything you've learned from the past topic, just apply it to your beams. The same thing, right? So let's do that. Again, we're at section AB. I'm gonna cut it. Already denoted here. Yeah, you're gonna cut at those sections. Then you're gonna isolate either the left or the right side, whichever is easier. Now for here, it's gonna matter what side you're gonna take. Okay. So for section AB, obviously the left side is easier to isolate, right? So let's isolate left side. Okay. Isolating that, draw a line. You have an applied force, RA. And then length would be important here. So denote your length as length x, right? And then here, again, our goal is to create shear and moment equations. You're going to guess the direction of your shear force. So for shear force, right, this this element, yeah, this side still needs to be in equilibrium. Okay, so again, make an intelligent guess. If this is upward, therefore my shear reaction would be downward. Okay? And your moment would counteract the moment of created by your external forces. So you have your RA here. Okay, you're taking shear and moment at this section, at this end. So taking moment here, this RA moves clockwise at about this point. So to counter that, to keep this in equilibrium, your moment should be opposite of that. So it should be counterclockwise. Alright? And then apply your equilibrium equations. Let me move this here. Summation of moment equals 0. So may a moment, forces first. Summation of forces, y equals 0. So RA minus V equals 0. Again, we're looking for V. So V equals RA. So I need, and RA is 18. So 18 kilonewton. And then, our answer is positive, therefore correct assumption. Now to get the sign convention of V, okay, we're gonna check if it's clockwise or counterclockwise. So V, okay, about this beam, so V would be clockwise, right? About this beam, therefore positive. 18 kilonewtons, positive. Okay? Next, how about moment? So same thing with moment, summation of moment equals 0. I'll just move this. Yeah. Summation of moment equals 0. R, again, moment about this segment. So RA times distance x, right? And positive since clockwise. And then V is at this segment, so no bearing. And then M here is counterclockwise, so minus M. Okay, the actual direction of your moment equals 0. So M therefore is just RA times X. And RA is 18, so it's just 18x unit kilonewton meter. Then positive, therefore assumption is positive. Now to get the actual sign of your moment, check whether it is concave, upward, or downward, or if it makes a smiley face. So imagine this M, okay, it's this direction, then gonna hit this portion. Therefore, the tendency of your beam is to move this way, right? Since it makes a smiley face, therefore positive. Next, let's move on to the next side, which is segment BC. Okay? Actually, dito naman. BC. And again, you're gonna cut and determine what side is easier or what side you want to solve, left or right. Now, as a rule, okay, if you're gonna create, because later on part B, you're gonna create a shear moment diagram. You want to take your equations from one side only. So I started with the left, so this should be on the left side as well. But you can use the right side, but I'll show you the difference later. So isolating left, this is again RA. Okay, and then as you can see, there's an applied force here, 14 kilonewton. Okay. In case, by the way, in case RA, RD are not given, you can just solve that using summation of forces vertical and summation of moment equals 0. Here it's given to eliminate that process. So again, RA, okay, cut here, isolate that. There's only two forces there, right? And then this distance is 2. And then take the distance from your support to where your cut is as X, right? Then figure out the direction of your shear and moment. So again, make an intelligent guess. This is 18 upward, 14 downward. To make this in equilibrium, I need another force downward. So assume V as downward. Okay. Next, moment. Okay. So RA greater than 14, 18 greater than 14. So you're gonna have an excess moment. Okay, upward, then about this point, this is clockwise. To make that in equilibrium, I'm gonna guess my moment is counterclockwise. Okay? And let's see. Summation of forces y equals 0. Where A minus 14 minus V equals 0. So V equals RA minus 14. 18 minus 14. So that's just 4 kilonewton. And my answer is positive, therefore correct assumption. And now check whether this B is clockwise or counterclockwise. So about your beam. So making it rotate about your beam, it's clockwise, therefore positive. So your equation is V equals 4 kilonewton, and it's positive. Next moment. Okay. Okay. I'm going to put this back. Okay. So lastly, side CD. Okay. So as you can see, CD, cutting it here, easier to take the right side, right? But if you're gonna make a shear moment diagram, you have to take it from the same side as you did in the first one. So left. So CD left side. Okay, and then draw again. So this is RA. This is 14. Again, just isolating the left side. And this is 28. Okay. Oh wait, I haven't solved it. Sorry. Going back to BC, summation of moment equals 0. Here. So starting with the left side, RA, about this clockwise, so positive, then distance F, RA times X. Next 14, about this side is counterclockwise, so minus 14 times distance. This distance is now your distance X minus 2, right? So X minus 2. And then M is counterclockwise, as you can see, so minus M equals 0. Okay, therefore solving for M equals RA is 18. So again, 18x minus 14x minus 28. Okay, then simplifying. 18 minus 14, that is 4x. So you get 4x. This is plus 14, negative 14 times negative. 4x plus 28. And obviously this is positive. Therefore, correct assumption. And then to check for positive or negative, look here. And so moment, if you follow this, the tendency of your beam is to move this way. So this is positive, concave upward. There. Done. And then lastly, segment CD. So this distance is 2, this is 3, and then as usual, distance of support is x. Then guess. So RA is 18, downward 14, downward 28. To keep this in equilibrium, I need another upward force. So my guess is shear is upward. Next, since the greater external force here is downward, okay, it's gonna create and figure out how is it gonna rotate about your segment. It's gonna rotate, as you can see, counterclockwise. So therefore, to counter that, my moment should be clockwise here. So clockwise is this way. That's it. Okay? Operator equation, summation of forces, y equals 0, RA minus 14 minus 28 plus V equals 0. So V equals 14 plus 28 minus 18. That's negative 20. Yeah, that's 24. Right? Yeah, that's 24. Positive, therefore correct assumption. So 24 kilonewton meter. Now check, is this clockwise or counterclockwise? So from your V, again, try to rotate it about your beam. Yeah, it's going to rotate this way, and that is, as you can see, counterclockwise. So counterclockwise, therefore your shear force is negative. Okay. Then next, M. Summation of moment equals 0. Okay. So to get this, so let's start with the leftmost side again. RA, it's clockwise about this side, so RA times distance x. Then 14 is downward, rotating it about this side. Again, you get counterclockwise, so negative 14. Distance to this side would be, we're going to take this length, that's x minus 2. And then lastly, 28. 28 downward, rotating it about the right side, you get counterclockwise. So again, negative 28. Distance, I'm gonna take this distance, which is just x minus 2 minus 3, or x minus 5. Okay? And then we're not done. M. So M is clockwise, therefore positive, and equals 0. Okay, solving for M. M is equal to 18 times x, or A is 18, right? So 18 times x minus 14x minus 28x. So that is negative 24x. Okay? And then 14 times 2, 28, positive 28, plus 28 times 5, that is 168. So plus 168 kilonewton meter. So unit for moment, kilonewton meter. Then, okay, so x here, let's see if this is actually positive. This can't be greater than 3, 4, 5, 6, 7. Okay? So if we compute 24 times 7, that's 168. So negative 168 is the limit of this. Okay, so it can't get higher than 168. Therefore, if you add these two, you're just going to get a positive number as well. Okay, again, x, the greatest number x can have would be 2 plus 3 plus 2. Okay, which is 7. 7 times 24, that's 168. So negative 168 plus 168 is 0. And since x can't be 7, actually it's less than 7, the answer here will always be positive. So correct assumption. Now let's check, is it concave upward or downward? Let's see. Moment. Okay? You think this moment's gonna hit here, right? Therefore, the tendency of your beam is to move this way. Right? You get a frowning face, sad face. But this is negative. Okay? So that's part A, we're done. Next, part B, draw shear force and bending moment diagram. So here's an intro to that. We'll get more into that later. Okay. Get part B. Let me move this here. Yeah. Okay. Hmm. All right. So pardon, it looks a bit crowded. Okay. Okay. Part B. So to draw shear and moment diagram. So let me just recreate that. So you have your, this is 18, this is 14, this is 28, and then this is 24. Okay. You get shear and moment diagram. This is what you will do. Draw your segments, which is basically just where your forces are applied and your reaction. Okay. Then 2, distance 2, 3, 2. Okay. So let's start with shear diagram. All right. Shear. So to start off, you're gonna draw your reference line. Okay, so let's say this is your reference line, right? And then this is your shear diagram, okay? So just look at your external forces. You're gonna start at the leftmost side where you started your equations with. So I started at left, so start at left side. So this is your 0, 0 point. So from 0, look at your forces. This is upward at this point, so go upward as well. So you're gonna go upward by how much? By the same amount your external force is. So this is 18. Okay? Zoom in. So 18. Next. When there is no external force applied, that's just a straight line. Okay? Yeah. Next, look here, there's another external force applied downwards. So you're gonna go the same direction. You're gonna go downward by 14 units as well. Okay? Therefore, if I went up by 18, then I went down by 14. Okay, this height would be 4, right? So this height is still 18. Going down, this is now 4. Okay, so this is 4. And then next, From 4, I went down another 28. So going down by 28. Okay? Therefore, this length would be, okay, so 4 minus 4 is 0 minus 24. So this is negative 24. Okay, again, how did we get that? From positive 4 minus 28. Since downward, you get negative 24. And again, no external force, so just a straight line. Then you get here, positive 24, so you go upward. Negative 24 plus positive 24, you get 0. And this is how you know you created a correct shear diagram if you started with 0 and you end at 0 as well. Okay? So that's your shear diagram. And this is for B. Next, for M. How did you do that? Same thing. So from N, for shear, you base it off here. So for N, I'm going to base it off here. Okay? So again, you're going to start at 0. Your 0, 0 mark. So from 0, this is what you'll do. If your shaded area, so we call this area, if your shaded region or area is above your reference line, so therefore positive, the slope of your moment diagram will be positive as well. So meaning this is positive slope, this is negative slope, right? Do that, positive slope. By how much? So this point will be now the area of this portion. And again, we'll go more into that later. So this is just 18 times 2. Right? So 18 times 2, that's just 36. Or, equations here, right? Let's check. As you can see, shear at AB is 18. It's correct. From point A to B, that is 18. So let's write A, B, C, D. Okay. So yeah, it's correct. A, B, 18. Next, for BC, shear is 4. And yes, shear is indeed 4. And then for CD, shear is 24. And yes, you can see the value of this is negative 24. Negative. Okay? So it follows the equations that we created. So now let's do that for your moment as well. Okay? So let's use our equation instead. So moment, let's start with AB. So moment is 18 times x, kilonewton. So that's an equation of a line, diagonal line. Therefore, drawing a diagonal line, then what is x? X is the length of your beam. So at this point, x is 2, so 18 times 2, again, that's 36. So yes, it's the same. Okay? Let's try it again for BC. So BC is 4x plus 28. Positive, therefore, upward slope. Okay? So 4x plus 28, and now what is my x? Is 3. So 4 times 3 plus 28, you get 40. Oh, no, no. Yeah, you get 40. Hmm? Sorry, x is not 3, it's 5. Sorry, x is from R8. Okay, so 4 times 5, 20 plus 28, you get 48. So another upward slope. Actually, let's make this smaller. Okay, 36. Another slope. Okay, so this is 48. And if you check, to get the area of this, that's 4 times 3, 12. 36 plus 12 is also 48. And then next, let's look at this equation. It's negative, therefore downward slope. and it's negative 24x plus 168. So negative 24x is 4, 3, 4, 5, 6, 7. So negative 24 times 7, 168. Negative 168 plus 168 is 0. So that's another indication if your moment equation is, or your moment diagram is correct. If you start at 0 and end at 0. That's how you draw it. Now what if I took, or I isolated the right side? What's going to happen? So let's see here. So let's check for CD. But right, okay? What is that going to look like? So CD for the right side. So draw that. You get this. You get an applied external force of 24 or RD. And there's nothing else. Okay? And then, to make this in equilibrium, I'm going to guess that my shear force is downward. And then, your 24 will create counterclockwise moment. So to counter that, I need a clockwise moment here. Okay? And then this distance is x. Create your equation. Summation of forces y equals 0. So negative v plus 24 equals 0. V equals 24. Positive, therefore correct assumption, kilonewton. Then C, is this clockwise or counterclockwise? So it's counterclockwise. So this is negative. Okay. Next, moment. Starting from the right, again, 24 creates a counterclockwise. So negative 24 times distance x from this end. And then you have an applied or reaction moment clockwise. So plus m equals 0. So m equals negative 24, sorry, positive 24x, positive, therefore correct assumption, and to get the sign, okay, so your moment gonna hit here, it's gonna bend this way, so it's a happy face, therefore positive. So why is it like that? Here our moment is negative, here it's positive. Well, that's because you took it from a different end. You took this from the right side. So let's see. If you start at the right side, again, because this is the right side, you start at 0. Positive, therefore upward slope, meaning this way. Okay, that's your upward. Downward would be this way. So upward slope. And then by how much? It's 24 times x. And here our x is 2. 24 times 2, that's 48. Okay. So as you can see, it's the same thing, right? The only reason why they have different signs is because you're going to start at a different way. Okay. From the left, okay, here to this point, you have a negative slope. From the right, this point to this point, you got a positive slope, right? So that's the reason why. Let's also look at your shear force. This is negative, therefore that should be below your reference line. Same thing with this negative, therefore V is below your reference line. So yes, they're both. CD is both below reference line. Then in your equation, if V is positive, and V is positive, meaning it's above your reference line. So as you can see, A, B, and BC both have areas above your reference line. So those are the things you need to think about for your shear end moment. Okay, do you have any questions? So do you understand? Please answer yes or no. All right, great. Let's move on to the next topic. So what I described earlier is called your area method. Okay, so you have two ways to get your moment diagram, shear moment diagram. One is by equation. The other is what I've been doing first is your area method. So let's talk more about your area method. So first, let's consider a distributed loading over your beam. Okay, so it's subjected to a line load of intensity W of X. That just means your intensity is applied over a length X. Therefore, you get the following differential equation. So weight, or not weight, intensity equals differential V over differential X, and shear force is equal to differential N over differential X. So how do we get that? Let's look at the derivation of these equations. Okay. Okay. So first, we're gonna take an element. So this is the element taken. So dx is an infinitesimal length, okay, meaning an extremely small segment, extremely small length, dx. Okay, again, remembering your differential calculus. Then you have this, a differential intensity as well, w dx. When you convert this to a point load, remember to get point load is just w intensity times length. That's why it's w dx, all right? W dx. So on this side, you're gonna get moment M and shear force V, okay, to counter this load. And then to react to that, you also get, you know, your moment M on the right side and shear force V on the right side. So the reason why this is M plus dm, because over this small area, you get a differential moment. That's why dm. Same thing with shear. Over this small area, you get an additional shear, dv. Okay, so from this figure, you're going to create your equilibrium equation. So summation of forces vertical equals 0. Okay, so therefore V positive minus point load W times length, so W times dx, minus, since downward, V plus dV. So you get V minus V cancels out, negative W dx equals dV, therefore intensity is just negative dV over dx. Okay, next, how about moment? Same thing. Summation of moment equals 0. So here M, clockwise, right? Therefore positive. Then V, okay, we're taking moment about point O, so about this. So V about point O is also clockwise, so positive. Distance from V to point O is dx. Therefore V dx. Next, point load about O, that is counterclockwise, therefore negative. Okay, point load is W dx. Then distance from point O, it's this length right here, or this, which is just dx over 2. Since point load is at the center of your distributed load. Okay. And then moment, this is counterclockwise, therefore minus. So minus m plus dm equals 0, right? So simplifying that, you get v dx, since m cancels out, right? V dx minus w dx over 2 times dx over 2 minus dm equals 0. Now, multiply everything, divide everything by dx. You get v minus, okay, this cancels out dx over dx, so you get w dx over 2 minus dm over dx equals 0. Now, dx is a very small area, very small segment, okay, infinitesimal. Since this is very small, you can just say that 0, okay? So therefore, v minus dm over dx equals 0, therefore v is just dm over dx. Differential moment over differential length x. That is just how those equations were taken. Now, okay, going back, so from these equations, this is how the analysis of your area moment method or area method is taken. Okay? So theorems relating load, shear force, and bending moment diagram are as follows. First, load intensity at any section of the beam is equal to the negative slope of the shear force diagram. Next, shear force at any section is equal to the slope of the bending moment diagram at that section. Next, the difference between the shear forces at two sections of a beam is equal to the negative of the area under the load diagram between those two sections. So in short, that means VB, V any point on the beam, equals VA minus area W. Okay? And then difference between the bending moments at two sections of the beam is equal to the area of the shear force diagram between those two sections. So again, taking section A and B, MB equals MA plus area of your shear force diagram. Then lastly, shear force diagram is 1 degree higher than that of the load diagram, and the bending moment diagram is 1 degree higher than the shear force diagram. Well, what does that mean? So let's take an example, okay? So let's do this. Let me zoom out. Ulit natin to. Okay. So let's say again I have a beam, right? And let's say we have a distributed load. Okay, so this is what your distributed load is. It's uniformly distributed. And the intensity W is 10 kilonewton per meter. Okay? And then let's say this length is 2 meters. So get your reactions first. Since this is uniformly distributed and since this is symmetrical, reactions are easy. It's just 10. Get your point load. So that's 10 times length. So 10 times 2, that's 20 divided by 2. So that is 10 kilonewton, 10 kilonewton. Okay? Right. So let's start. Let's do this one by one. So load intensity at any section of the beam is equal to the negative slope of the shear force diagram. So let's draw first our shear force diagram. I already taught you how to draw that, right? So we're going to start with left side usually. There's 10 kilonewtons upward, so go upward from 0. So by 10. So this is now 10. Okay? If there's no load, you're going to get a straight line. But here I have a uniformly distributed load. What you're going to get now is 1 degree higher than that. Okay? And shear force diagram is 1 degree higher than load diagram. So I have a straight line, 1 degree higher than that is a sloping line. Okay? So our forces are downward, so go downward. Okay? Till you reach the end of your distributed load. Okay? So going downward, get this. Then you're gonna wonder how much do I go downward? So it's 10 minus the point load, total point load of this. So it's 10 times 20. So 10 minus 10 times 20. 10 times 2, that's 10 minus 20. So that's negative 10. Okay? So you're gonna go downward until you reach negative 10. How about your distributed load? So at the end of this, you get negative 10. And then go upwards since you have an upward slope here. Okay, so upwards plus 10, so you end at 0. So I have a correct shear moment diagram. Now let's check. Right? Load intensity, or W, negative slope of your shear force diagram. So writing that, so W, negative slope, so that's change in Y over change in X. My boundary is 10. It's already given. So let's check. Is 10 equal to negative change in Y over change in X? Let's see. Change in Y. So this is my slope, right? Slope of my shear force diagram. So that is rise over run. The rise of this is negative 10, or 10 minus negative 10, right? So negative 10 minus 10. Final point minus initial point over change in X. Run is 2, so 2. So 10 negative 20 over 2. So yes, negative 20 over 2, that's positive 10. First theorem correct. Next, shear force at any section is equal to the slope of the bending moment diagram at that section. Now I need to draw the bending moment diagram. So bending moment diagram is 1 degree higher than your end. Bending moment diagram 1 degree higher than shear force diagram. My shear force diagram is a sloping line. What's 1 degree higher than that? Say, parabola. Parabola. So how do I draw that? So same thing. If your area is above your equilibrium, your reference line, slope of your moment diagram is positive. If it's below, slope of your moment diagram is negative. Okay? Let's draw a line here to denote the change between a positive area and negative area, right? So here, area is positive since it's above your reference line. So the slope of my moment diagram should be positive as well. And this is the slope of a parabola. So positive slope would be this way. Okay? So positive slope, and draw it until you reach the 0 mark. And then I don't know the point of that yet. Okay? Let's not solve it. All I know is it starts from 0. And then we're going to go downwards. Since your area is now below your reference line for the shear diagram. So downward slope of parabola is this way. So going downwards, get something like that, right? So let's say you don't know how to get the slope of a of a parabolic line, parabola, right? Instead of using this theorem, let's use this. Okay? So VB equals VA minus area W. Okay, so let's try. What if I want to take this point? Okay. Let's call this point B. Want to know the shear force at point B. So it's at this end. So let's say VB equals VA minus area of your load diagram. No, moment. No. Let's not take moment first. We're looking for shear force, right? Shear force is slope of bending moment. I don't know how to do that yet. So instead, I'm going to use this. So shear force equals VA minus area. So let's say I want to know shear force at B, right? So area, your load diagram. So meaning I want to take the area of this point. Okay? So VB equals VA minus area. So what's VA? So taking 2 points, 2 sections, VA here, is your VA. Right? Why did I take that as A? Because I already know shear force at this end is 10. Because that is just where your reaction is. Okay, so 10 minus area of your load. So this area right here. Okay. So area of this portion, that's just a rectangle. Height of this is 10. Okay, so W means just the height. So that's 10 times base. And my base there is, let's say that's 1 meter. Okay. So times 1. I don't know, that's, let's say 0.5 meters. Since this is 1 meter, so that's 0.5. So 10 minus 10 times 0.5, you get 5 kilonewtons. So shear at B is actually, this point is now 5 kilonewtons. Okay. So that's proving this theorem. Try using this equation on other points, you're gonna get the shear force at that end. Then the next difference between the bending moments at 2 sections of the beam is equal to the area of the shear force diagram between those 2 sections. Okay. So let's say I want to know moment at B. Right? It's just the area of your shear force. So let's solve moment at B. Let me delete this. Okay. So moment at B is just moment at A minus area. Minus area of your shear force. So moment at A, I know that's 0 since you're at your support. This is a pin support. There's no moment there. So 0 minus area of this. This is a trapezoid, so that's just base 1 plus base 2 over 2 times length. So 5 plus 10 over 2 times length, this is 0.5. Okay, computing for that, you get minus, plus. So 5, and this 3.75 kilonewton. Therefore, this is 3.75. Now, what if I want to take the maximum moment of this beam? Then you're going to take it at the highest slope of your bending moment diagram. So here, let's call that point C. So summation of moment at C, again, you're just going to take the area between two segments. So it's smart to take it at, it's smart to choose your A as a support. So again, this is my A. So MA minus area B. And MA0, a plus. So 0 plus area between A and C. So this is the area between A and C, that's a triangle. So it's 1/2 base times height. So 1/2 base. Base of this is 1 meter, right? Since this is at half. So how do I know this is the half point? Usually, if you have a uniformly distributed load, your shear force or shear force diagram will hit 0 mark at the center of that. That's why this is 1. Times 1/2 base, again, that's 1. Height of this, as you can see, it's 10. So equals 5. Okay? Kilonewton meter. Therefore, this point C is actually 3. There. So that's how you analyze a shear moment diagram. Okay? So usually it's just the area of the diagram above it. Do you have any questions for area method? So do you understand area method? Please answer yes or no. Right, great. Next. Now, let's talk about what if you have a distributed load. Now, what if you have a concentrated force and a couple? If you remember from your MEC30, couple is just two forces that are parallel to each other, creating a moment. So the analysis is the same as your distributed load. You still have this. Okay, so you're gonna go through that differential calculus derivation. You're gonna get the equation VA plus. So plus just means on the right. So shear force on the right equals shear force on the left minus your point load. Then moment. So moment on the right equals moment on the left plus your couple. This is an example of a couple. This is an example of your point. So it's basically the same. So look here. Here's a summary of the moment diagrams or the diagrams of different types of load. So let's start here. You got no load, but you have couple. Counterclockwise couple. So your shear there is constant. There's no force, right? When there's no force, you just get a straight line. Okay? And then your moment, remember, if you have your moment is always 1 degree higher than your shear. Okay, so from none to a straight line, 1 degree higher than that is a sloping line or diagonal line. So you got a diagonal line. And then, so for this point, from starting from the left, since your area is above your equilibrium line, you have a positive slope, right? So positive slope upward. Then you have a counterclockwise moment. So counterclockwise is negative, so you're gonna go down. Okay? And then on this portion, your area is still above your reference line. So you're still gonna go upward slope. Next, what if I have what is this? A cantilever beam with a point load at the end. Okay? So again, this is your equilibrium line. There's gonna be a reaction here. This is downward, therefore reaction here is upward. So from 0, go up. There's no force present, so this is just a straight line. Then there's a force downward, so going downward. Right? Next, your moment. So there's gonna be a moment reaction here. This is taking moment about this end, you're gonna get a clockwise moment. So to counter that, moment here would be counterclockwise. Okay? So starting here, your 0 point, you have a counterclockwise reaction, so you go downward. So going downward. Next, your shear diagram is a straight line. So your moment diagram is 1 degree higher than that. That's a sloping line. Your shear diagram is above your reference line, so therefore the slope of your moment diagram is positive. So go upward. And then there's no other moment there. Next, you have a cantilever with a uniformly distributed load. So again, you're going to have a reaction of shear force reaction and a moment reaction. So shear force, your forces are downward, you're going to have an upward reaction. So go upward. Okay? You have a uniformly distributed load, 1 degree higher than that is a sloping line. Okay, so downward, so therefore sloping line downward. Until you get your final point. Next, how about moment? So this distributed load, convert to a point load, is still downward. Rotate it about your support here on the left. You're going to get a clockwise moment. And again, to counter that, you need a counterclockwise reaction. So counterclockwise here, that's negative. So from reference point, go downward for your moment diagram. Next, this is a sloping line. 1 degree higher is a parabolic line. And then this is above your reference line. So slope of your parabola is upward. Till you get 0. Okay? Next, how about a point load? So point load, you have that. So reactions here and here. Reaction here is upward. Then you get a straight line. Then minus whatever force this is. Okay, then you get another straight line. Then upward at the reaction here. Next, moment. So this is a straight line. 1 degree higher is a sloping line. So from 0, this is above your reference line. So upward slope. Okay. Then at this point, it changes to a negative area. So downward slope. So downward. Okay. Next, uniformly distributed load with simple supports. The reaction A at here. Okay. So you go upward. And then you have a downward uniformly distributed load. So you go downward 1 degree. So that's a sloping line there. Okay. Until you reach whatever value this is at this point. Then you have another upward reaction. So you end there. Okay. Then your moment, positive area 1 degree higher. That's a parabola. So positive slope for a parabola. Then you end at this point because it changes to a negative area. So negative slope. And then lastly, what if you have a linear distributed load? This is an example of a triangular load. So again, reaction, reaction. So reaction upward, so you get upward. This is a sloping line, so you get a parabolic line. Okay, so this is downward, therefore downward slope for a parabola. So which is again this way, right? So this way, so you go downward. Okay, until you reach the total magnitude of this intensity, load intensity. Then you got a reaction here, so you go upward. Okay? Now you have a parabola. What's 1 degree higher than that? Your second degree parabola. Or we call that cubic. So second degree parabola, positive area since above your reference line. So again, positive slope. At this point, it turns into a negative area, so negative slope. There, so that is the analysis of different types of load, shear, and moment. Now let's have an actual example. The simply supported beam in the figure supports a 30 kilonewton concentrated force at B and 40 kilonewton couple at D. Sketch the shear force and bending moment diagrams by the area method, then neglect the beam. So our goal is to get your shear moment diagram. No problem with that. Let's see. So first off, draw your beam. Let's zoom in. So first things first, reaction is not given, so I need to solve for reaction first. Okay, let's solve. So let's start with, I'm gonna take moment at point A. Yeah. Summation of moment at A equals 0. Okay, let's start. PB, clockwise, therefore positive. So positive 30 times distance 4. Next, this is a couple and it's clockwise, so that's positive. So just positive 40. And then you have your reaction at supports. So you have reaction A, reaction E. So at rollers, there will never be a horizontal reaction. At pin, there could be a horizontal reaction if you have a horizontal force present. But there is none, so I won't draw that anymore. So it's just that way. So next, RE. RE about point A, that's counterclockwise. So minus RE, distance is 4 plus 3 plus 3, that is 10. Therefore, please solve what's RE. Ready your calculator so that we can solve quickly. What's RE? Correct, Julius and John. Yeah, 16, yes. Kilonewton. Next, I want to know RA. So that's just summation of forces vertical or Y equals 0. So RA upward, positive, minus 30. Then that's not a force. So plus RE equals 0. And what's RA? 14, correct, Evangelist. Mark. Okay, next. Now from that, I can draw my moment diagram. Let's start with shear. Again, you're going to start at 0. You're going to go up by RA. RA is 14, so go up by 14. Next, there's no force, so just draw a straight line. Next, okay, so make guides for portions where there is a force applied or a couple. Okay. So you have a straight line up to this because now you get 30 kilonewton force. So go downward by 30 kilonewtons. So 14 minus 30, what is that? DD. 14 minus 30 is the answer. Correct. Negative 16. So this is negative 16. Okay. Next, we get a straight line again. And this doesn't bother us. That's not a force, so just go straight. There's no other force there. And as you can see, RE is upward, so go upward. And what's RE? 16. So negative 16 plus 16, you end at 0. So this means you got you did your shear force diagram correct. Next, let's do your moment diagram. So again, this is shear. So this is moment. So moment start at 0 since there's no applied moment at your supports. So 0. Next, this is 1 degree. So you go a sloping line. This is above your 0 mark or your reference line. So this is upward slope. So upward slope. Okay. Next, what is this value? So let's call that MB, right? MB. Remember, MB is just the area above it. So it's just MA plus area B. So 0 plus area of this, it's 14 times distance of this is 4. Now what's 14 times 4? 56, correct. Kilonewton meter. So this is 56. Next, you have a negative area. So you go down. Okay, then you stop when you get a couple. So how do I know what's that? Let's call that MD. MD1. Okay. So what you're gonna do? So MD1 now is just your MD. Okay. Let's take this segment. So MD minus B minus AB. So MB is 56 minus. So here, um, so for now, you're gonna ignore the couple. Just stop there. Okay. So 56 minus area of this, which is this is 16 times length of this, it's 3. So 56 minus 16 times 3, that's 8. Okay. Therefore, when you draw this, again, negative area, so you go downward to 8. So now this is 8. Next, that's when you apply the effect of your couple. So your couple is clockwise, therefore that's positive. Therefore, your moment diagram will go upward. So you're gonna go upward. By how much? So by 40. Okay. So let's call that ND2. So it's your 8. And then just add your couple, which is 40, and that's 48. Yeah, 48 over here. Next, okay, basing here, again, you still have a negative area, so you're still gonna go downward. By how much? Let's call that ME. Okay, so don't always assume you're gonna end at 0. You still need to solve to make sure you're doing it correctly. Okay. So ME is now just, let's take this segment, MD minus area B. What's MD? 48. You're gonna take the higher value, right? So 48 minus area of this. Well, not the higher value, rather. They're gonna take the point where you stopped. I stopped at 48. Okay, so use 48. So 48 minus area of that is just a rectangle, so that's just 16 times length 3. So 48 minus 16 times 3, you get 0. So That means I did things correctly. I'm ending at 0. Okay? That's it. There. That's your shear force diagram and moment diagram. Any questions for number 1? None? Okay. To understand number 1, please answer yes or no. Alright, great. Let's continue. Last problem for today. And it looks a bit complicated. Let's see. The overhanging beam in the figure carries 2 uniformly distributed loads and a concentrated load. Using the area method, draw the shear force and bending moment diagrams for the beam. Neglect the weight of the beam. So straightforward, just draw the diagram. All right. Okay. So again, first step, find out your reactions. So let's call this RB, and let's call this RA. And remember, there's no horizontal force, so there's no horizontal reaction of your pin support. Okay, so I want to solve for reaction, so let's start with moment. So let's take moment at B. You can start with moment at B, you're going to get the same thing. If you want to practice, do that. So summation of moment at B equals 0. So how do you do this? First, convert all of your uniformly distributed load into point loads. So how? Just multiply it by its length. So 400 times length 2 feet. So that's 400 times 2, 800. 800. Then this is at the middle of this. So this is 1 feet. Do the same thing here. 200 times 4 plus 2. 200 times 6. That is 1,200, right? So let's choose a different color. Yan. 800 times 800 pounds. Then distance. This is 1. Same thing here. Yeah. This is 1,200 pounds. What's the distance? So this is for 6 feet. Middle of that is 3. So this is 3 feet. Okay, this is also 3 feet, right? Now let's start. Let's start with the leftmost side. So we get 800. So 800 about B is counterclockwise. So negative 800 times distance from B. As you can see, that's 1. Next reaction at B at point B 0 is, sorry, moment of RB about B is neglected or is not considered. Next, PC. So PC about B is clockwise, so plus 400 times distance between them, it's 1 feet. Next, and your point low, 1,200, again clockwise, so plus 1,200 distance. This is 3, then you got an additional 1, so 4. Okay, and then lastly, RA. RA about B is counterclockwise, so negative RA. Distance is 4 plus 1, so that's 5. Equals 0. Right? Solving for RA, you get 880 pounds. Next, for RB, it's just summation of forces Y equals 0. So you're still going to consider your point load, negative 800 since downward, plus RB minus PC, which is 400. So that's right, that minus 400 minus 1,200 plus RA equals 0. Solving, oh, why did I call that RA? That's RB. 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 Solving for RB, You get 1,520. Okay, let's draw. So again, you're gonna create a line for every slide load. Okay. Starting at 0, okay? So you have a downward force, so you're gonna go downward. By how much? By this area. So 400 times 2, that's negative 800. Next, you're gonna go upward by RB. RB is 1520, negative 800 plus 1520. I believe that's 720. Okay, oh, let's call that. VB1. VB1, 0 minus 400 times 2, negative 800. VB2, again, this is 1, this is 2. Negative 800 plus reaction RB, 1520, 720. Next, so this is straight line since there's no applied force here. Next, go down by 400. So you're at here. And how much is that? So let's call that BC1. Okay, so from 720 minus 400, that is 320. 320. Next, okay, we're gonna go down to RD by how much? Let's solve. Okay, since this is a straight line. So let's call that VD. VD1. So VD1 equals 320 minus area of this. That's 200 times 4. So 320 minus 200 times 4, that's negative 480. You're at a negative, you're gonna go below your reference line. This is negative 480. Next, you have a reaction at RD. Let's call that BD2. So negative 480. Upward, therefore, plus RD, which is 880. Negative 480 plus 880, you get positive 400. So go up by 400. This 400. And then again, you're gonna go downward by a slope. So that's VE. So VE equals 400 minus area of this, which is 400 times base, which is 2. Okay. Sorry, that's 200. Intensity 200. So that's 0. So you end at 0. So meaning, I did this correctly. That's your shear diagram. Next, let's try if we can finish the moment diagram. Okay. So again, start at 0. There's no applied moment here. This is below your reference line, so slope is negative, as well as 1 degree higher, it's parabolic. Okay. So how much? So MB is equal to, this is a triangle. So it's just MA plus area of your shear force, so 0 plus 1/2 base, 2 times height, 800. So 0 minus 1/2 times 2 times 800, you get negative 800. So this is negative 800. You go down, parabolic slope, negative 800. Next, you have positive area, so you go upward by this area. So let's call that MC1. Oh, no, just MC. So MC equals MB plus AB. Negative 800, okay, plus area. So this is an area of rectangle 720 times 1. So negative 800 plus 720 times 1, that's negative 80. So you're still at the negative, but this is an upward, this is a positive area, so you go on upward slope. And this is your upward slope. Okay? So this is your negative 80. Next, add it by this area. Now the problem there is I don't know this base. Okay? I'm gonna make that, let's call that x. To get that area, it's 1/2 base times height, so 1/2 320 times x, right? So let's call that, and let's call that f. MF. Because I can't just get the area of this. I need to account for the change in positive to negative area. So MF is just 320, negative 80 plus area of this. And see, it's 80. Negative 80 plus 1/2 base times height 320. And I don't know x. I'm gonna make that your homework. You can solve it or not, up to you. But I'm gonna leave it to you, solve for x. Then we'll continue this next meeting, alright? I'm gonna ask you next meeting, what's x? So do you have any questions? Again, try to solve for x if you want to. I'm gonna give plus points to those who do. Yes, question about the project. It's due on tomorrow. Tomorrow. Anything else? Okay. Alright, sure, yeah, no problem. You can just resubmit. I'm just gonna consider the latest submission. Any other concerns? Okay. Gonna continue this on Thursday, so obviously there's no quiz show. I'm sorry about that. Lecture, then on Saturday your modular exam. Okay, so since you don't have any more questions, you may go. Goodbye, class. It's fine. If you're late by a minute, doesn't matter. 19 ba? Alright. So 19. So Friday. Friday deadline of project. If you don't have any more concerns, you may go. Goodbye, class.